Bismillahirrahmanirrahim. Assalamu alaikum students. Hopefully you will be fine and doing well. So in last week you have learned about the Newton's forward difference approximation to find the derivative of a given data, then Newton's backward difference approximation. So in this week we will learn about the central difference approximation. So we will see that how we can approximate our rate of change of a given data with the help of central difference approximation. So in today's lecture we will learn about Gauzes backward central difference approximation. As in previous lectures you have learned that in central difference you have further different approaches to deal your data to find the rate of change. So Gauzes backward central difference is also a technique to approximate the rate of change of the given data. So here again you have two options. First, you can interpolate your data with the help of Gauzes backward central difference approximation, and then you will get a polynomial in a variable like x, and then you can differentiate that particular expression with respect of independent variable, and then you can find the rate of change at any point by substituting that fixed value. So the other way is that first we will construct a formula to find the first order derivative, second order derivative, and then we can use directly that formula to approximate the rate of change of the given data. So in this lecture first we will revise Gauzes backward central difference interpolation formula, then we will construct a difference table for the Gauzes backward central difference approximation. Then in next stage we will try to develop an expression for the first order derivative for the Gauzes backward central difference approximation, and then the second order derivative, and at the end we will use these formulas to find the rate of change of a given data. So we will see that in an example. So Gauzes backward interpolation. As I have told you before that Gauzes backward interpolation is a type of central difference approximation. In central difference approximation, if you want to approximate your data near the central point, near the midpoint you can say, then we prefer the central difference approximation. In central difference approximation there are the different techniques. So Gauzes backward interpolation is one of them. In Gauzes backward interpolation actually we move backward from the central line. Actually this is the central line. Here x naught is a central point we choose, that is in the midpoint, and this is the value of the function at x naught. So this is the central line and this is above the central line. So in Gauzes backward we move backward like this from y naught to del y minus 1, then we go to the next step del square y minus 1, then we will again go back to del cube, then del 4, and then del 5, and then at the end we can reach at del 6. So in this way we can move in the Gauzes backward interpolation formula. As in Gauzes forward interpolation formula, you have learned that you can move in the forward way. So in Gauzes backward interpolation formula involves odd differences above the central line through y0 and even differences on the central line, and these are the differences, these are the odd differences above the central line, and these are the actually even differences on the central line. So this is formula for the Gauzes backward interpolation. As you have learned this before in numerical analysis 1. So we mostly try to use this formula when we have a p, that is x minus x naught divided by h, is greater than minus 1 and less than 0. So this is the difference table. In first table you can see that we have constructed a difference table with the help of forward difference operator, and in the second table you can see that the entries in the same difference table has been replaced with the central difference. So actually the values of the difference table will remain same, but the position with respect to the forward difference operator and with respect to the central difference operator will be the different. So we can use both of them. Mostly the forward difference operator is used in the Gauzes backward interpolation formula. So in sometime in some books central difference operator can also be utilized. Here you can see that this is the central line, x naught, y naught, and this is backward position, del y minus 1, del y minus 2, del y minus 3, and this is the forward position, del y naught, del y1, del y2. Similarly in the second order difference, these are the backward positions and these are the forward positions. So this table is constructed with the help of forward difference, and similarly this table is constructed with the help of central difference. Just like you can see here that here the indices y0 and this is y minus 1. So you can get this position by adding these two terms and then divided by 2. In indices you can see that by adding 0 and minus 1 and divided by 2 you will get minus 1 by 2. Similarly by adding minus 1 and minus 2 you will get minus 3 by 2, and similarly other differences, central differences can be obtained in the same way. Like if you want to obtain this central difference operator, you can add 1 by 2 and minus 1 by 2, you will get 0. Similarly if you want to get this difference, fourth order difference, so you will add minus 1 by 2 and minus 3 by 2 and then divided by 2, you will get minus 1. So this table can be constructed in the same way. So here the formula of the Gauzes backward central difference approximation, first in equation 1 is written in the form of forward difference operator. So here the same formula in the form of central difference operator. So here you can see that this is the position, y0 has the same position, y0, del y minus 1 is replaced by del y central difference y minus 1 by 2. Similarly forward difference, second order forward difference, minus at minus 1 is replaced by the second order central difference at 0 at naught position. Similarly, forward difference, third order forward difference operator at -2 is replaced by third order central difference operator by at -1. Similarly, the fourth order forward difference operator at -2 is replaced by fourth order central difference at y0, and in the same way you can replace all the forward differences equation 1 with the central difference operator. So here in equation 2 all the forward differences operator are replaced with the central difference operator. So now let's come to our main point, that is how we can find the rate of change with the help of Gauzes backward approximation. As in last slides we have learned about the Gauzes backward interpolation formula. So here we will construct a first order derivative for the Gauzes backward interpolation formula by using the same interpolation formula as we have learned before. So now again differentiating equation 1, and this is actually the equation 1, that is the Gauzes backward interpolation formula. So we will differentiate equation 1 with respect to x, as the equation 1 contains all the variable in term of p, and p is also depending upon x. So here to find the derivative of the function with respect to x, first we will use chain rule. First we will find the derivative of the function with respect to p, and then we will differentiate p with respect to x. So this is the chain rule: f prime at x is equal to df by dx is equal to df by dp dv by dx, and that is equal to 1 by h df by dp, where p by dx is actually the 1 by h. As we know about the expression that p is equal to x minus x naught divided by h, so once we will differentiate p with respect to x, we will get 1 by h. So by using the value of dp by dx that is 1 by h, and we will get the expression 1 by h df by dp. So finally we will find the derivative of the function that is given in equation 1 with respect to p. So after finding the derivative of the function and substituting here, we will get the expression given in equation 2, that is 1 by h is equal to forward operator difference operator of the function at -1 del y minus 1 plus 2p plus 1 divided by 2 factorial del square y minus 1 plus 3p square minus 1 divided by 3 factorial del cube y minus 1 plus 4p cube plus 6p square minus 2p minus 2 divided by 4 factorial del 4 y minus 2, and up to so on. So to find the second order derivative, we will differentiate equation 2 again with respect to x, and to differentiate this with respect to x, first we will again use the chain rule. First we will differentiate the function f prime with respect to p, and then we will differentiate p with respect to x, and again we have the value dp by dx is equal to 1 by h, and just we will find the rate of change of this function with respect to p, that is given in equation 2 here. So after finding the value of this expression df prime by dp and substituting here, we get another expression that is for the f double prime at x, where x is any x is any point near the central point here, and p is equal to x minus x naught divided by h. So let's discuss a special case, and that is that if we want to find the rate of change of a function at a center point, exactly at a center point, that is x is equal to x naught. If we have a x is equal to x naught, then we can find that p is equal to x minus x naught divided by h is equal to 0. And if we put p is equal to 0 in first order derivative in equation 2 and in second order derivative in equation 3, we get the following expression, that is f prime at x is equal to, and here actually the x prime at x naught, x prime at x naught is equal to 1 by h del y minus 1 plus 1 by 2 factorial del square y minus 1 plus 1 by 3 factorial del cube y minus 2 and up to so on. And similarly the second order derivative at x naught is equal to 1 by h square del square y minus 1 minus 1 by 12 del 4 minus 2 plus up to so on. So finally, as we have learned about the first order derivative with the help of Gauzes backward interpolation, and similarly we derived the second order derivative with the help of Gauzes backward interpolation. So now we will use both to find out the rate of change of a given data near the center point. So here you can see that we have a data that so the values of x are 0, 1, 2, 3, 4, and at the same node points the values of y means the function values are 5, 0, 9, 38 and 93, and we have to find y prime at 1.9 means near the center point, and we have to find y double prime at 1.9. This is actually the central line, so we have to find the rate of change near the center point. So obviously we will use a central difference approximation scheme, and in central difference approximation scheme if we see that p is equal to x minus x naught divided by h, that is equal to, here the x is 1.9 minus x naught is actually 2 divided by, and h is the difference between the consecutive values of x is 1, that is minus 0.1. So the Gauzes backward approximation fulfills its condition that p should be greater than -1 and less than 0. So here it's good to use Gauzes backward formula. So this is the difference table. In first column you can see the values of x, and in second column you can see the values of the function at same node points, and here in this column you can see the first order forward difference. Here h is equal to 1, x naught is equal to 2, x is equal to 1.9. This implies that p is equal to 1.9 minus 2 divided by 1 is equal to minus 0.1. So by using these values and the values from the difference table here, these values like del y minus 1, del square y minus 1, del cube y minus 2 and up to so on, by using these values, as we are choosing the Gauzes backward formula, so we will move in backward direction like y naught to del y minus 1, then del square y minus 1, then del cube y minus 2 and up to so on. So by using these values in equation 2, and after simplification we will get a rate of change of a required data at point 1.9, that is 16.1017. Now we will proceed to the second order derivative at point x is equal to 1.9, and that is f double prime at 1.9 is equal to, here h is equal to 1, and these are the values taken from the table, and after using these values in equation 3 we get f double prime at 1.9 is equal to 19.4. So students, today we have learned about the Gauzes backward difference approximation to approximate the first order and second order derivative, and in second part we have solved an example that how we can utilize that formulas to obtain our results. So now you have an assignment. You will construct a polynomial in variable x by using the same data given in example 1, and then you will find its first and second order derivative at point 1.9, and then you will compare your results with our previous results. So these are the results, so you will compare your results with these results. Thank you students.